what a nice view. Wait, where am I?
Here, take a look at this. What is this? This is a mobile GPS tracker. It can show your location in real time, plus your speed and direction.
Oh, cool. How does it work?
Well, this device is part of a system called the Global Positioning System, or GPS for short. It communicates with at least 4 satellites. Each satellite sends a signal, and the device receives it. By timing how long the signal takes to arrive and multiplying that by the speed of light, which is about 299,792,458 meters per second, it calculates the distance to each satellite.
Okay, but how does that help me?
Each satellite essentially draws an imaginary circle around itself, with the radius being that distance to you. The point where all these circles intersect is your exact position. This process is called triangulation.
Oh, I think I get it. But this just shows where I am relative to the satellites, right?
Yes, and that's why each satellite carries an atomic clock, extremely precise clocks that keep time by measuring the decay of radioactive elements. They use this to know exactly where they are in orbit. The satellites convert their position to a coordinate system called Earth-centered, Earth-fixed, or ECF, which is then translated into longitude, latitude, and altitude that you see on your device.
Wow, that sounds complicated. But where did all this come from?
All right, time for a quick history lesson. Ready?
Sure.
The world's first artificial satellite. Scientists noticed that radio waves sent from Sputnik were stretched or squeezed because of the Doppler effect. This gave rise to the idea that if you can track a satellite's signal changes, you can figure out your position on Earth. In the 1960s, the US Navy developed the Transit System, an early GPS version. It helps submarines navigate the oceans when underwater, since they can't use visual landmarks. But Transit had long wait times and limited accuracy. Fast forward to 1973, the US launched Project Navstar, the modern GPS precursor. It was crucial for all military branches. The Army needed precise tank locations, the Navy had to know where ships were, and the Air Force needed exact plane positions and to guide missiles. Speaking of missiles, during the Vietnam War, F-4 Phantom II jets struggled with bombing accuracy. Ballistic computers helped, but they couldn't account for crosswinds. Laser-guided bombs were introduced, but they required a clear line of sight. Clouds could block the laser. GPS changed the game by guiding weapons precisely to their target, regardless of weather. Between 1978 and 1985, Block 1 GPS satellites were launched as prototypes. By 1993, the full 24-satellite constellation was operational. Initially, civilians didn't have access to GPS. Then came a tragedy on September 1st, 1983. A Korean Airlines Boeing 747 strayed 500 kilometers off course and entered Soviet airspace. The Soviets scrambled a Su-15 interceptor, shot down the plane, and 269 people died. To prevent this, President Reagan made GPS available to civilians, but with selective availability, SA, which intentionally reduced civilian accuracy. SA was turned off in 2000 after it became clear troops in the Gulf War were using inaccurate civilian GPS devices, risking their lives. Now GPS has a maximum error under 3 meters, used daily by billions worldwide.
That's incredible. But how did they get all those satellites into orbit?
Great question. Launching and deploying GPS satellites is a complex process involving rockets, precise orbits, and a bit of space choreography. The first prototypes, Block 1 satellites, 10 in total, were launched by Atlas E and Atlas F rockets. These were repurposed ICBM rockets adapted for satellite launches. The satellites were carefully placed into medium Earth orbit, MEO, about 20,200 kilometers above the Earth's surface. After the early successes, the Block 2 satellites, which formed the full operational constellation, were launched mainly on Delta II rockets. The Delta II was a workhorse rocket famous for reliable launches from the late 1980s into the 2010s. Here's how a typical GPS satellite launch goes. Rocket launch. The rocket carrying the GPS satellite blasts off from Earth, aiming for a precise insertion point in space. This first stage burns fuel to escape the dense lower atmosphere. Staging. After the first stage burns out, it detaches to lighten the load. The upper stages ignite and push the payload higher and faster. Orbit insertion. The rocket's upper stage delivers the satellite into a temporary orbit. For GPS, this isn't the final orbit, but a transfer orbit, typically elliptical. Orbit raising. Using onboard propulsion, the satellite fires thrusters to circularize its orbit and reach MEO. At this altitude, it travels around Earth every 12 hours. Deployment and calibration. The satellite deploys solar panels, antenna, and atomic clocks. It then undergoes a calibration period to ensure accurate timing and position data. Operational entry. After testing, the satellite joins the GPS constellation, where it works with the others to provide continuous global coverage. The Russians have their own system called GLONASS, launched by Proton-M and Soyuz 2 rockets, which orbit satellites at similar altitudes. The Chinese run Beidou, launched mostly on Long March 3B and 3C rockets, and Europe's Galileo satellites fly on Ariane 5 and Soyuz rockets. GPS satellites have a lifespan of about 10 to 15 years. When they age or malfunction, they don't just drop back to Earth. Instead, they use onboard propulsion to boost themselves into a graveyard orbit, a higher orbit where they won't interfere with active satellites. It's kind of like retiring to the space equivalent of a safe neighborhood.
Isn't that wasteful? All those old satellites just floating around?
It is a bit, but right now it's the safest way to manage orbital traffic and reduce collisions. Space junk is a real concern. Researchers are working on ways to safely deorbit satellites, but it's tricky when you're thousands of kilometers above Earth. Additional details. The science of satellite orbits and GPS signal latency. At MEO, GPS satellites strike a balance between coverage and signal delay. Signals take about 50 to 600 microseconds to travel to your GPS device, depending on the satellite's position. That's nearly instantaneous, but must be precisely timed because even a tiny error can throw off location accuracy by hundreds of meters. The atomic clocks on board these satellites are marvels of engineering. They keep time to within a billionth of a second, allowing GPS to calculate your position by measuring the time delay of signals with extreme precision. Fun fact: the space race's hidden GPS influence. Did you know the GPS system wouldn't exist without the Cold War? The arms race pushed the US military to develop better navigation for missiles and planes, which eventually spun off into civilian tech we use every day. In fact, some early GPS tech was repurposed from missile guidance systems.
Are there any safety measures to stop rogue states from misusing GPS for missiles?
Yes, there's something called the COCOM limit, from the Coordinating Committee for Multilateral Export Controls. It restricts GPS usage above 1,000 knots, about Mach 1.5, and above 60,000 feet altitude. If a device meets these conditions, GPS signals shut off for that user. China also distorts GPS coordinates within its borders, deliberately shifting positions to prevent exact targeting or spying, a form of digital defense.
This is amazing. From war satellites to helping me find coffee, GPS really changed everything.
It sure did. Every time you use your phone's map, hail a rideshare, or track your run, you're riding on decades of innovation and some of the most precise engineering in history. It's a global system that quietly powers the modern world.
And to think, it all started with a Soviet satellite and some radio waves.
Yup. Now, next time you look at your GPS, remember, there's a whole army of satellites orbiting 20,000 kilometers up, timing their signals perfectly so you never get lost.